Okay, so far we learned how to identify the feedback control gain K of the posture control joint torque, one by the regression methods and the other by the forward simulation. And then those identified gain could explain observed posture strategy change from ankle to hip as a function of perturbation. In this chapter, we are going to introduce the optimal control perspective to describe the human posture control. Okay, since this optimal control is a new concept for the first year graduate student, because we don't cover this concept for the undergrad control courses, I'm going to briefly introduce what is the optimal control and its formulation. Okay, as a control engineer, suppose you want to design the controller, you want to select the gain, you want to select the closed loop pole, desired pole to satisfy the performance goal. What else you should consider? You should take into consider. Yeah, the cost, right? So even though your controlled designed control could satisfy the performance, you should also satisfy the spec for the motor, the maximum torque that motor could generate, or even the energy, like all the energy consumption for the motor to perform those control. So control cost is also an important factor to take into account. So to place the closed loop pole from the for example, a single inverted pendulum has a mirror image unstable pole. Maybe one way to do it is just move this unstable one to next to your stable one. So move to the mirror image. Would you satisfy those response? If yes, that's okay. This would be the one that you set the design. Maybe you prefer more faster responses. Okay, so whatever you have a further from the origin, you have a faster response, but that requires larger control input. Okay, so if you examine the control input magnitude, it will be greater. So you should make a judgment which one should you choose. Or maybe you could do something else, like maybe you can do the complex conjugate instead of two pairs at the rear axis. Okay, so which will guarantee certain amount of the zeta, the angle here. Okay, and the response, the distance from the origin. So maybe some complex conjugate pair could guarantee the control cost perspectives and the response perspective. So there are infinite number of way to define or determine the closed loop pole. So to satisfy both performance and the control cost, maybe I'd like to minimize the error and the cost altogether, right? So minimize this value. Mathematically, to do a minimization or maximization, the quadratic form could be used. So I can also minimize the error square and the cost square. That's the concept for the optimal control. So instead of satisfying the goal for your control, you also care about the control cost. So by setting the aim, the objective, J, as error square and the cost square, and then you design the controller that will minimize this objective function. Often it is called the cost function. Okay. So let's formulate the optimal control minimizing the cost function or the objective function. So I'm going to briefly introduce what the state space form from the equations of motion. Equations of motion so far we handle is based on the ordinary differential equation form. Okay, but to make it as a matrix form, I'm going to set a state vector, okay, as a theta and theta dot here, and rearrange everything in terms of state vector x. Okay, so to do so, I have to be able to formulate the theta double dot. So I rearrange the theta double dot in terms of theta and theta dot, which is a state in the input term t. Then your theta dot matrix, the vector is going to be expressed by the certain matrix multiplied by the x and certain matrix vector and multiply the input. So here we call it as an x dot, and that's A matrix, and that's a B matrix. That's the state space form of equations of motion. Okay, so x dot equals ax plus bu. Here u is state feedback, is minus kx, or kx with the k as a minus value. So I'll just use it interchangeably. So how to find this gain K? Gain K, as we mentioned earlier slides, so minimize the objective function, minimize the not only the performance, but also the control cost. Okay, that's the goal. How we can do it? How we can do, find the gain K that will minimize J. To formulate this, this is how we formulate using the linear quadratic regulator problem. So by setting the cost function, not only just having the error square and the cost square, you have a weight function, so Q value and the Q matrix and R matrix here. Okay, so Q matrix penalize the X, the error. Okay, so if you suppose that you have a Q value something like 100, what that means is since you want to minimize the J, if Q is a large value, you can bear the great amount of the x. You really want to reduce the x a lot because q already has a greater value. So what that means is you really want to reduce the x value by minimizing the k, by minimizing the objective function. For r, that penalizes control cost. So by having large r value, that means even though you have a really small u value, control input, the total j becomes large. So you really want to very strictly reduce the u value, which means you want to set the control gain k that has very, very small control effort. Okay. So how we can find the gain k? Mathematics found out to formulate them using the closed form, the analytical form called algebraic Ricard equation, ARE equation, ARE equation. So that's written as this way. So this is quadratic for x, okay? Quadratic for x, and everything else is given. Like A is a system matrix, AB, and then Q is what you are. Q and R is what you predetermine for the optimization problem. Okay, so by solving this AR equation, your solution for that can be plugged into R matrix and the B matrix to calculate the optimal K. So if K is determined this way, that will minimize this cost, the AQR problem. Okay, that's mathematically proven. So let's use this for a simple example, like a single inverted pendulum. Okay, so this is ARE equation, and then this is the optimal gain K obtained from the solution for the ARE equation X. Equations of motion for single inverted pendulum is written as this, right? And then state space form will be a theta in theta dot. So we have a x dot equals to the ax plus bu, the state space form of the equations of motion. Now, let's set the q and r. Okay, make the problem simple, let's just make the q as 1, 0, 0, 0. What that means is I only care the error for the theta. Okay, the first term is penalizing the theta, the first state variable theta. So I'd like to make the small theta as possible. And then for the r, what that means is the total magnitude of this value will the penalty for the control input. So if rho is really, really large, that means your r is going to be almost 0. That means you don't really care about the cost for the control. So, as far as the performance is satisfied, just do a lot of control. This is what that means. Okay, so by solving ARE equation, we have this relationship like x21 is going to be x22 square, and then x21 can be solvable by this second order linear equation. And plug that value x here as for optimal gain k, what you ended up having is this one. And then if you plug this one here and here to here, your final answer for the optimal gain k could be analytically solved as a function of rho. Okay, the sigma is a system value that you never change. So you have a rho value. So as you have a greater rho, greater k. So greater rho means chief control. So gain increases. That makes sense. Okay. Okay. So let's just examine the value. Okay, like putting just a real value. Oh, by the way, so if you want to implement it for the optimal control in MATLAB, you just type in LQR. Okay, RQL, the input variables are system definition, like by A matrix, B matrix, and so on. So just look for sys in MATLAB to how you can define the system. And then you just plug in your input, predefined Q and R matrix that will give out the optimal gain K. So for simplification, let's just say sigma equals to 1. If your penalty is 1, your optimal gain K is this value. If you have a great penalty for that control input, your gain decreased, right? I think this is the minimum control gain K that will satisfy the behavior, the system performance. And if you have a really small penalty, means you don't care about the control cost, you could see that your control gain increased, right? So that's intuitive. So if you look at those closed loop pole trajectory in the root locus in S plane this is original open loop pole for the inverted pendulum. And if there's a very expensive control cost, then I would rather not do the control. This is what this optimal control means. And for small penalty, you will do the control. So this pole has been moved to here, some kind of complex conjugate value. Okay. And if you have a greater rho value, which means a cheap control, it'll increase the gain K, and then your response gets faster. Okay, so as far as you have a certain damping behavior, which is zeta equals to 0.07, 0.7, your closed loop poles are approached to this asymptote. Okay, so as you increase the gain, poles getting closer and closer, faster response with certain guaranteed damping. Okay, that's how your closed loop pole behavior for the optimal control example. Okay, so next we are going to study how this optimal control scheme could be used to understand human posture control.